Hey everyone, it's time to talk about friction. We've talked about friction a little bit as one of the four forces that we always say are acting on an object. We've talked about gravity, tension, normal force, and then friction. And the friction and the normal force are actually very closely related. Remember, a normal force is a force between two surfaces acting perpendicular to the surfaces. And friction is a force between two surfaces acting parallel to the surfaces. So friction comes in two types, static friction and kinetic friction. Now, static friction is oftentimes referred to as the friction of an object that isn't moving, and I don't like that definition. Static friction is the frictional force between two surfaces where the sliding is not taking place. It wants to take place, but because of friction, it cannot take place. Kinetic friction is going to happen when the two surfaces are sliding across each other. So a good example of static friction in a moving object is the tires in your car. When your car is moving, the frictional force between the road and your tires is generally static friction. As long as you're not peeling out or skidding, then the force between the tires and the road is static friction, even though the car itself is moving. All right, now, the frictional force is defined as, so I'll use a lowercase f for friction. And if I say, I'm going to start with kinetic friction, the kinetic frictional force is equal to some coefficient, and we use the Greek letter mu, and I'll subscript it with a k for kinetic, so the coefficient of friction times the normal force. So as an example, if I look at this block and I slide it across the desk, you can see that the frictional force is a little between 1/2 and 1. Keep in mind at the 0 point, that's 1/2, right? So that's just the scale is imperfect. But you can see that frictional force is somewhere between 0 and 1/2, between 1/2 and 1, which we subtract 1/2 for the scale. But if I put these bricks on top, then in order for this to slide, you can see that that's right around 3.5 is the reading there. So the frictional force is increased. Why? Because the normal force is increased. Right? If I increase the weight of the block by putting these two bricks on top, then I have increased the normal force. All right, real quick force diagram right here. There's the weight of the block down, mg, and then the normal force is up. Okay, the weight of the block is down, the normal force is up. So when I increase the weight on a flat surface here, when I increase the weight, I increase the normal force. All right, so the frictional force, which is going to be, I've got the tension in this direction, the frictional force is in this direction, and since it's sliding, I'm going to use kinetic friction. So when the normal force increases, so does the frictional force. To compensate, the tension has to increase, right? The tension has to increase. So that's the equation, and I stress the word equation, you'll see why in a minute, for the kinetic frictional force. One thing to keep in mind is that the coefficient of friction is generally not a single value. Oftentimes in the problems we'll tell you, hey, the coefficient of kinetic friction is 0.15. But in reality, the coefficient of frictions, kinetic or static, are a range of values. And that's because conditions are slightly different depending on what we're talking about. For example, I've done some work with car accidents, and I'll look at the coefficient of friction between rubber for the tire and the roads, and it usually ranges from like 0.2 or 3 up through 1 point something, and that just depends on the tire and the road. It's a huge range, and so you can't have a single value. It's going to be different for a bald set of tires than it is for tires with new tread. It's going to be different on chip sealed road versus asphalt versus concrete. Okay, so there's a variation in there, even with the same two materials, because the road over here and the road over here are going to be slightly different, okay? But we'll generally use a single value. Now, the equation, which is not really an equation, the inequation, if you will, because it's an inequality for static friction, is less than or equal to u static times the normal force. Less than or equal to. Now, why is that? So this is a real good demo right here. So as I pull on this block with the bricks on top, you can see that, okay, I zeroed out, doesn't matter what I zeroed, I can pull right now, there's 1 1/2 on the reading, So the force is 1.5, but the block isn't moving. So it's in equilibrium, and so in this case, this would be static. The tension, which is 1.5, and the static frictional force is the same. But if I pull a little harder out here to about 3.5, still isn't moving. It still isn't moving. And so the tension is 3.5, but the force, then the static frictional force is 3.5. Again, static because there's no sliding taking place between those surfaces. So less than or equal to. The static frictional force will be as large as it needs to be, right? And then if I pull hard enough, I'll eventually get it to slide, right? The other thing to take notice of here, I'm increasing about 3, 3.5, 4, and then once I've reached that 4 mark, and notice it was almost 4.5 over here, right? And then over here, it's a little less than 4. So again, you'll notice right in these, just from right here to right here, that frictional coefficient has changed, right? That's why we work with the ranges. But you get it started at around 4, and then once I got going, I'm down to 3.5. And what's happening there is the coefficient of kinetic friction generally is smaller than the coefficient of static friction. And so once the object is going, it's generally easier to keep it going. All right? And that you know that from trying to push something across the floor. And go ahead and push a table or a chair across the floor, and you'll get a feel for that, right? If I push on this podium, I can push lightly and it doesn't move. Push more and it doesn't move, right? The coefficient or the frictional force, the static frictional force, maximizes at a huge amount. But once I've got it moving, it's easy to keep going. And this is on roller, so that's kind of cheating. All right, but you get the idea. All right, why is that frictional force there? Because there is, on the molecular level, these are not smooth, right? There's molecules, and they're rubbing against each other and kind of binding up against each other, and that's why you have friction. Your book will talk about that, but it's forces at the molecular level. Just real quick then here, let's do this one more time. Get this attached. So as I try to get this brick moving on the podium, it starts to move at around 4. If I put it up on that book, it took a little bit more to move on the book, and now a little bit less again. You can see that changes from one spot to the other. Okay, let's try the paper in the book. Now, looks like the coefficient of friction between the block, the wood of the block, and all of these surfaces are roughly the same. Roughly, a little humor there. Anyway, you get the idea, and it will be different between two different surfaces. It can be different. Let me rephrase that. It can be different, depends on the surfaces. If I were to do this on a smooth glass surface, we'd find the slide is different. Wood versus this tabletop, and then these steel bricks versus the tabletop, probably different. Okay. One thing that we can do is we can determine the value for the coefficient of friction. I can take one of these bricks, for example, put it on this book, and as I lift the book up and it tilts, you'll see the brick begins to move, right? And where that moving takes place, that free body diagram will kind of help me determine what the coefficient of friction is. We'll do that in a later video. All right, if you have any questions, please leave them in the comments below. Thank you.